Hi, everyone. Welcome to the Women in Data Science Datathon webinar, the first ever. We're really excited to have you and to have our special guests, Jennifer Marsman and Vani Mandava from Microsoft. This is going to be a really nice lunch hour for those of us on Pacific time and for those joining from all over the world or viewing this afterwards. I know it's not the most convenient if you're halfway across the world. Welcome. And we're glad to have you, and we hope that you will submit your questions and definitely share some of your input in the audience stats. It's always fun to see where everyone is in terms of their career trajectory, and I can think of no better role models on Love Data Week to spend lunch with than Jennifer and Vani. Jennifer is the principal engineer for AI for Earth at Microsoft, and Vani is the director of data science. Through my role as executive director of the West Big Data Innovation Hub, funded by the National Science Foundation, we've had the chance to work with both in the WiDS efforts and other initiatives, and it's so great to have both of them here to do some little jumpstart tutorial on machine learning and Kaggle and what this whole WiDS Datathon is about. So without further ado, I will turn it over to Jennifer.
All right, thank you so much, Meredith. I'm very excited to be here with you guys. So what we want to do is introduce a new Kaggle challenge to you. So I'm going to kick us off with a short introduction to some basic information around machine learning. So this is going to be very introductory content. I saw there are a few experts on the line with the incoming poll. So for you guys, this may be repeat. But for those new, I just wanted to kind of lay the foundation and talk about a couple of different concepts that could potentially help you with this challenge, like supervised learning and transfer learning and some of these things that could help. Then if you have any questions, feel free to put them in the chat window. And then Vani's going to give the second half of this presentation, and she's going to talk specifically about that Kaggle challenge. So feel free to just throw your thoughts into the chat window now, and then while she's speaking, I'll go through and answer all of them there. Okay, so right here. All right, so my name is Jennifer Marsman. I'm the principal engineer on the AI for Earth team at Microsoft. And I just want to give you a quick intro of some of the basic content that you need to know to be able to understand the palm oil challenge. First of all, let's talk about a kind of an overview of machine learning. Should start with some of the different types of machine learning. So there's a couple different types out there, big categories. Supervised learning is a very big one. Supervised learning is used when you want to do predictive analytics. So if I had a whole bunch of historical data about, say, the price of a home is an example I love to use. Then what you can do is take historical data about, various homes and the actual prices they sold for, and then use that historical data to be able to make future predictions. So that's really all supervised machine learning is doing. There's also unsupervised machine learning. And so what you can do with unsupervised machine learning is make sense of a lot of data that doesn't necessarily have to be labeled. And what I mean by labeled is in the case of our predicting a house, we needed to know the actual price for those various homes to be able to move forward. But with unsupervised learning, you don't necessarily need a label. You can just kind of have a whole bunch of data and then maybe cluster similar things together or look for like relationships. So it's great when you're kind of given a large data set and someone says, Jennifer, go make some sense out of this. You could maybe form some groups and explore the data using unsupervised learning. There's a couple other types of semi-supervised learning, reinforcement learning, which is a turn-based where there's an agent which can take several actions which affect an environment, and then you can have the environment get into different states which may have different rewards associated with them. And so that's another form of machine learning that you can utilize as well that is very popular. If you've seen anything with the AlphaGo work that was done, that was all reinforcement learning as well. So a lot of cool different types of learning. But today, what I want to focus on is supervised learning. That's what you would use for something like the palm oil challenge in Kaggle that we're going to talk about. So supervised learning is used to make predictions, like we said. It does require a labeled data set, again. So we have to know for the thing you're trying to predict, what those values are for some historical data. And then it can help you answer a whole bunch of different types of questions, like whether a customer would like a certain product, for example, or it could tell you a number. It could predict, here's the kind of, here's the value that your electric bill might be based on historical usage and weather patterns and things like that. So in supervised machine learning, let's dive into that one a little bit more deeply. I mentioned that it could predict a couple different things, like a number. If it is predicting a value on a continuum or a number, that's called a regression problem. And so you can use it to do things like predict a sales number, predict the cost of a home is an example of regression, those sorts of things. You can also predict between several discrete buckets. So I have a picture of an animal. Tell me, is that an elephant, a giraffe, or a zebra? Who's going to win the big game? You know, this team or that team? Am I going to develop a certain illness in the next 6 months? Yes or no? So those kind of things are extremely useful and can be done with supervised learning. All right, so how does it work under the covers? Let me show you a quick example. And again, I'm going to go back to my favorite example of predicting the cost of a home. Now, as I said, in order to do this, you do need a historical data set. So here's an example of a whole bunch of historical data, and I actually grabbed this data from Zillow. So this is real data of various prices of homes in Chicago. Now, it is a labeled data set, so I do need the various prices that these homes would cost. So there's a number of different things that would affect the cost of a home. So the size of the home might be one thing, the area. The zip code, location is very important for how much a home would cost. The number of bedrooms, the number of bathrooms, the number of years since someone remodeled the kitchen, the size of the master bathroom, all of these things might be relevant. The quality of the school district, maybe. So all of these things could factor into the price of that home. So we want to capture as much of that data as possible that could make an impact. So doing that, we then are going to basically develop a mathematical model for how to be able to predict this in the future. Now, think back to, you know, if you've done any kind of like linear regressions. Remember AX plus BY plus CZ in college or in university? So you can use that same idea of having weights assigned to those various features to be able to make a prediction. So we could even do something similar if these were all straight numerical values, something times like maybe the area times some weight plus, you know, the number of bedrooms times some weight, the number of bathrooms times some weight. Those all could factor into the cost of the home. So you can kind of visualize it in your head of that's approximately what that mathematical model could do. So how do we do that? How do we figure out what those weights would look like? So that's what's called a training of the machine learning model. So there's really two key phases that you'd use. The first is training, and that's when we actually find the relationships between our label, which is the thing we're trying to predict, such as the price of the home, and all of the features. And those are the things that could affect the cost of the home. And then, so there's then after we've kind of developed this mathematical model, so we have the features and the label, and then all machine learning algorithms do is use crazy beautiful math to find the correlations between those features and that label. And the kind of crazy beautiful math that you're using is dependent on the kind of algorithm. So there's a number of different algorithms you may have heard of. Bayesian algorithms, neural networks, decision trees. All of these different types are different types of machine learning that have different math under the covers, but basically all that math does is find those correlations. Now, we're going to use some data to build that mathematical model, but we don't actually want to use all of our data. And here's why. If I build a let's say I have a ton of data here, and of course we would need way more than 4 rows to actually do this effectively. So let's say I have, you know, 1 million rows of data, for example. Now, in order, if I had trained a model based on all 1 million of those rows, and then I wanted to see how well my model performed, and I put in some row of data, it might do okay on that because that's one of the data, that's a data point that I use to train it, right? It already knows the answer. So the real test of how well your machine learning model performs is how well it can do on data it's never seen before. So that's why when you have, in machine learning, the hard part is often just getting a nice labeled data set like this. So when you have a wonderful golden data set like this, what we typically do is split it up and we hold back some of the results and only train with the majority of the data, but still not all of it. And so when I went to school for machine learning, when I was in grad school for machine learning, what we typically did at that time was a 70-30 split. This was like 15 years ago, so things have changed a little bit since then. A 70-30 split still works well a lot of the times. If you do have, in the era of big data now, where people can, if you have an IoT scenario or something where you just have a ton of data, then, you may not need as much as 30%. A smaller amount may actually be sufficient to test all of your areas. But, so there's a lot of different ways you can do this. There's also something called class validation, where let's say I have a big data set, and if I choose, let's say, a K of 10, let's say I split my data set into 10 equal chunks, and I train with 9 of them, and then test with that 10% that I held out. And then I could do that with a different 9 and test with another one that I held out. So you can do that, 10 times, holding out different chunks each way and see how the models perform and choose the best one. So that's another mechanism for doing this. So lots of ways to do it. So we use a subset of our data for training and then a small amount held back for testing. All right. And just to make that a little bit more visual and talk through this, let's do some pictures. And this is using an example of custom vision, which Vani is going to talk about in just a second. Custom vision is a tool that's provided by Microsoft that you're welcome to utilize for this channel if you so desire. And so if we kind of look at what we're actually doing during the machine learning process, we start with our training phase. So we have training highlighted here. And during the training phase, let's say we wanted to create a classifier that could differentiate between cats and dogs. Well, first we would put in a whole bunch of images labeled with cat, that were cats, and then a whole bunch of dog images labeled with dog. And then we create from that mathematical model. And then at test time, or when we actually want to use our model, what we can pass in then is a unlabeled image. So now we just pass in an image, and then if it's been trained sufficiently, then that model should be able to predict that that is in fact a dog. All right, so that's a visualization of the training phase and the test phase. All right, another thing to think about is precision, recall, and accuracy. So how do we measure our machine learning models? And most of the time you hear about accuracy, which is a great measure to use in a lot of scenarios. So in order to do this, we actually need to talk about, let me move this for a second. We actually need to talk about the various types of, let's make sure everyone is familiar and comfortable with the definitions of true positives and true negatives. So I'm going to give an example here. Let's pretend that we're trying to predict the likelihood of whether someone has a disease. And you can see I have a little table on the right-hand side that shows actual versus predictions. So if they actually have the disease and we predicted that they have disease, that's a true positive. If they actually don't have the disease, but we predict that they do, that is a false positive, and so on and so forth. So true positives and true negatives are good because our algorithm came up with the correct thing. False positives and false negatives are bad because our algorithm did not give the right answer. So one very easy metric to determine how well your machine learning model is performing is to take the true positives and the true negatives, so the answers that it got right, over all of the answers, and that gives you your accuracy number. Now, why would people ever want to use anything other than accuracy? That seems to make a lot of sense. It's a very legitimate thing to use. Well, we do also have these things called precision and recall. And there's actually another metric called the F1 score that actually combines. It's the weighted mean of both precision and recall. So why would we ever want to use those? When does that make sense? Well, the answer to that is, let's take the scenario where the disease we're trying to predict, this is probably the textbook example that's used in every single college textbook across the nation, across the world. The example of a very, very rare disease that only affects 1% of the population. So I could actually build a machine learning model that always returned, no, you don't have it. And that model would be right 99% of the time. but it would never actually get it wrong, right? So in that case, accuracy would not be the best measure to use, because if you just went on accuracy alone, you could very easily build a model that's 99% correct, but it would never actually catch any of the instances where someone does have the disease. So that's where something like precision and recall come in. And so if you look at the little chart here below, you can see that precision and recall would catch a scenario like that. Precision is the true positives over the true positives plus the false positives, and recall is the true positives over the true positives plus false negatives. And so they're actually like a weight. So when you raise the recall, your precision tends to go down, and vice versa. They're opposite sides of the same scale. And so you can think about it like the example that I show on the slide below. We could choose to have, in general, if we got an answer between 0 and 1, that could potentially be a decimal number, we could say that we predict that someone does not have the disease if it's less than 0.5, and that they do have the disease if it's above 0.5. You could also kind of tweak for precision and recall in the following ways. If we chose to predict one only if it was above 0.75, then you'd be predicting that someone has the disease only if you're very, very confident. And so that might make sense in a situation like cancer, where radiation and chemo are very hard on your body, and you don't always want to, treat someone unless you're sure they have it. Or the other way, which I think actually makes more sense in this scenario, is to go make sure you don't miss situations where people have cancer. So in that case, you might predict that they do have cancer if it's above, say, 0.25, and that will avoid you missing too many cases of cancer. So it helps you avoid false negatives, because of course you don't want to tell someone that they don't have cancer when in fact they do. So you can see how these other metrics are also useful for machine learning to be able to help develop a good, well-rounded algorithm that performs well in lots of situations. All right, so Vani and I are from Microsoft. We do have a couple ways that Azure could help you specifically when you're working on this awesome Kaggle challenge. One is that Azure does provide $200 in free credits. There's a free trial for anyone to use, so feel free to take advantage of that at azure.microsoft.com/free. And then there's a couple of tools that might be of interest, particularly for this challenge too. There's custom vision, which Vani is going to talk a little bit more about in a second, and it can do solve image classification as well as object detection problems. We also have a data science virtual machine. This is an amazing resource, you guys. It has all of the tools and frameworks and everything that you would want to use for machine learning, all set up and ready to go. I love it all the time. I use it for a couple of reasons. Number one, you may have a certain deep learning framework that you prefer, of PyTorch and TensorFlow and the CNTK and all of the different great ones out there. And so maybe you find a sample in a different deep learning framework that you don't have it installed on your machine, but it looks like it kind of solves your problem exactly the way you want, and you'd really like to just try out that sample code. Awesome. You use a data science virtual machine because you can spin it up. It's got all of the frameworks already installed. You can try out the sample code, maybe try your data on that sample code, see how it performs, and then decide, if you want to move forward with it. So I use it for that. The other thing that's great too is if you want to use like distributed training in the cloud, you can spin up a whole bunch of instances of this data science virtual machine, and it's already got Anaconda installed on it. It's got R and all the R tools, all the common Python libraries that you might want. It's got, TensorFlow, all the deep learning frameworks. So all the stuff, and plus a bunch of tools as well. PyCharm, all kinds of good things already installed on there and ready to go. So really nice for training at scale and for trying different samples and all kinds of goodness. And then one final thing that may be useful is something that we were formerly calling Batch AI, and it's now been bundled into our Azure Machine Learning service as it's called Azure Machine Learning Compute. But essentially what it allows you to do is to train your deep learning and AI models at scale in the cloud. So that's another really useful tool if you want to be able to iterate quickly. You can just throw it at the cloud, have it run and train your model very fast on nice GPU machines, and then shut them down so you're not paying for them. Super easy. And there's a whole lot of other things as well. Feel free to check out the link. Okay, so let's talk very briefly about neural networks as well. So neural networks, what they are giving you, or what we do with a neural network, so that kind of mechanism, what you're doing is putting your inputs. So if we go back to that example of like the house, where we're trying to predict various aspects of the house, we would input our various features into this X1 and X2. Those are our input layers. Then we have a series of hidden layers, and essentially each one of these, there's all these nodes, and then connecting them are lines which represent weights. So basically, the way the math works is that you are summing all of the weights that are connecting you. So A1 would equal X1 times some weight plus X2 times some weight plus a bias as well. So what this allows you to do is be able to model really complex, interesting mathematical relationships that can help you make predictions like we saw before. And so that's kind of how they work. You've probably heard the term deep learning before. Deep really is speaking to the number of hidden layers that are available. And with deep learning, with things like automatic machine translation, for example, speech recognition, a lot of these hard AI problems have essentially been solved with deep learning. And all that means is that we have a lot of hidden layers which enable us to model really complex mathematical relationships. And then our output layer is what actually predicts, you know, dog or cat or whatever it is that you're trying to predict. Disease, don't have a disease. All right, so transfer learning. So the idea behind transfer learning, this is what custom vision is actually doing under the covers. It's utilizing transfer learning. So let's talk about that for a second. I have an image here. This is an example of a convolutional neural network, which we don't have time to talk about today, but it's something that's very commonly used for image processing tasks. And essentially what we do is we have this big neural network. And it's wonderful, and these work really, really well, but the one drawback of them is they do require a lot of data to be able to work well. So the idea is, what we could do, you saw that neural network, it's actually possible that in the earlier layer, so in the earlier layers, imagine we have tons of layers here. In the earlier layers, what it's actually doing with these image recognition things is finding edges, and then it's seeing shapes. And then it may be able to recognize, you know, things like eyes. And then by the end of the neural network, so the latest hidden layers, it's actually recognizing that, you know, 2 eyes and a nose and a mouth. So these shapes in this relative proportion is actually what is a face, detects a face. So what we can do, since instead of using a ton of data to be able to do that all the way from scratch, there are a number of known data sets and architectures that allow you to be able to leverage this and just take advantage of kind of the figuring out edges and shapes and some of the early things that any image detection problem is going to need, and then essentially just chop off the end of that neural network and then just train the end. That's called fine-tuning it. And so we can start with this great, something like ImageNet, which has already been trained on a ton of images, and then be able to, and there's a whole bunch of other ones as well, ResNet, Inception, there's a lot of VGG, there's a lot of very common ones that are out there. So what we do then is start with one of those models that have already been trained on a lot of data, and then we can just utilize the kind of chop off the end and then be able to apply it to our specific challenge, such as recognizing palm oil. So here's a quick example. If we had only, let's say, less than 2,000 images from a search engine, and let's say we manually labeled them either dotted, striped, or argyle, and we wanted to predict what new images were, that's great, but it's not enough data. Like less than 2,000 data points is not enough to train a deep learning model. So instead, we can use a pre-trained convolutional neural network using one of these architectures, and then just be able to retrain the end and then be able to actually accomplish it with much less data. So that's actually what custom vision is doing under the covers, and why you can use a whole lot less data with custom vision and still be able to get some great results. So now you know what's happening behind the scenes there too. I just want to close with a couple of resources. Feel free to take a screenshot of that or whatever you'd like, but these are a bunch of resources that Microsoft has available. The AI School, our Learn AI track, a bunch of professional programs for AI data science and data analysis. And then you guys all know about Kaggle competitions already, but I am a huge fan of Kaggle. It's really great because Kaggle, if you just want to learn and get better at machine learning, you really need two things. You need cool problems to solve, and you need data to solve them with. And Kaggle gives you both, so you can just focus on the fun machine learning stuff. So I'm glad you guys are all competing. It'll be super fun. And then there's a whole bunch of great courses out there as well. Andrew Ng has done a whole bunch of really good ones on Coursera. Fast AI is great too. There's a lot of wonderful resources out there to learn even more. All right, so that's it for me. I'm happy to jump on and take your questions, and then Vani will take over for now to talk about the specifics of custom vision and how you can use it for this challenge.
Well, hello everyone. Can you see my screen?
Great. Vani, I think you're good to go. We can see your screen and hear you.
Okay, great. Can you see the slide on my screen? Okay.
Yes, we can see the slides, and Jennifer and I will continue. Thank you everyone for adding your questions in the chat window, and the Q&A entry point will continue to paste some responses there.
Yeah. Hi, everyone. Thanks, Jennifer. So I'm going to do a quick introduction of the Kaggle Datathon competition. I'll give you an overview of the data, and I'll explain one approach to how you can go about solving this challenge using a tutorial style presentation. So my name is Vani Mandava. I work for Microsoft Research as a director for our data science outreach program. I had a lot of fun working on this challenge, and I'm sure that some of you who, especially those who haven't participated in a Kaggle competition before, will find the experience really useful. So what is this competition about? To give you a little bit of background, oil palm is a tree that produces palm oil, and it's mostly grown in Africa and South and Central America. Most of oil palm plantations are grown through deforestation, and this deforested land is predicted to grow by 53 million hectares by 2050. Obviously, it's a very big eco problem, and there's been an 80% decline, for example, in orangutan population in Borneo alone, because a lot of native primate species live in the forests where this deforestation is happening. So it's important to understand where these oil palm plantations are, and high-resolution satellite images combined with computer vision algorithms can help us do that. How do we map these plantations, though? So Planet and Figure 8, which are two different companies, in collaboration with the West Big Data Innovation Hub and the WiDS Datathon Committee, have created a data set for this challenge of high-resolution satellite imagery. And the problem that you have to solve in this challenge is to develop a machine learning model that will detect whether or not an oil palm plantation is present in these images or not. And we'll go into a lot more detail about what kind of images these are. So the challenge is right now open. The deadline to enter is Feb 21st. And if you are part of a smaller team, you can have a team of up to 4 people. You need to have at least 50% of them as female or identifying as female. And the submission deadline for your competition is Feb 27th. A big thank you to the partners, to our data partners who provided the data set and have provided the annotations that helped create this challenge. It's a non-trivial effort. So what exactly is in this data? It's a supervised learning problem, but one that involves images. There are 15,000 images in the training set, and there are about 4,000 images in the test set, and there are about 2,000 images in the holdout set. For your final submission, you need to combine the test set and the holdout set to submit labels for about 6,500 images. One approach to the solution is using custom vision. Jennifer gave you a brief overview of custom vision. What is good about custom vision is that it does everything for you. You don't have to write all this code from scratch. It's a platform service hosted on Azure that is based on some really sophisticated deep learning networks like AlexNet and ResNet. ResNet is the newest and most popular and well-performing custom vision or image classification type of deep learning methodology. It's a great learning tool for beginners, and the URL is customvision.ai that you see on the screen there. So the workflow is fairly simple. You upload images, remember dog, cat, so you upload those kind of labeled images. You train the model, and then you evaluate the model based on the training data that you have given it. Except in this case, instead of dog, cat, you have images that have oil palm and images that do not have oil palm based on the labels that have been provided as part of the data set on Kaggle. So there are three different options on how you could leverage the custom vision service. The first option is you just give it a try using the custom vision UI. You upload, train, and test your model using only the UI. The second option, which I have used, is using the API, and I'll go into why we have to do that. And the third is a hybrid approach where you can train your custom vision model, export the model that you have created into a different format, such as TensorFlow or something like that, and then play with it. That's something you would use if you were building an Android application. It's just a good option for you to learn if you're going to be using this kind of a service in your work going forward. So using the UI, what does this look like? First of all, you're going to have to download those Kaggle images locally onto your machine. So I've done that. You can get that from the WiDS Datathon Kaggle page. Just do a search for WiDS Datathon Kaggle. You'll get to the competition page. Go to the data tab, download the images. Once you've downloaded the images, this is what it looks like on my machine. The source is where I have my Python code, that's a new folder that I created. And the submission file, which is part of the data set, is a sample submission, just to give you an idea of what that final submission file needs to look like. The training labels is where those annotations are provided, or the labels, right? Remember cat, dog again. So which of these images is that of an oil palm and which ones do not have an oil palm? So there's the image ID in column A, that has oil palm, so 0 or 1, and then the score, which is the confidence with which the annotation is being provided for whether it's a 0 or a 1. So for the sake of simplicity, I'm going to call the has oil palm images as yes images and the no oil palm plantation images as no images, because the rest of this presentation makes heavy use of that. So using the custom vision UI, you upload an image or you upload a set of images for each of those two labels, yes and no. Once you upload that image, you give it the label that you know it has based on, remember the training labels file that you have. So you need to separate those two sets out, first of all, and then you just click on this button in the custom vision UI that says train. In this particular example, because this is a manual process, I uploaded 29 yes images and 30 no images. And after I was done training, I checked the performance of this model. And behind the covers, the beauty of custom vision is that it actually uses k-fold validation, cross-validation, and it uses whatever images you've given it, comes up with a value for k, and does the training and comes up with the best model. Now, in this particular case, you have 15,000 images that you can potentially use to train. We've only used about 59 images. You got a precision and recall, which isn't that great. But when I did a quick test with just that small number of images, it did a good job in identifying that this particular image does not have an oil palm. You can see over here, the probability is 100. And the test is just up there in the predictions part of the UI that you see on the screen. So let's increase the number of images that we give the service, right? So you give 101 yes images, 99 no images, and train again. And again, all this takes 10 minutes, 5-10 minutes. So you are up and running, and you created a fairly powerful custom vision image classification model using nothing but a few UI clicks. And that is the learning part of this, right? It's really cool, and it's really exciting to see that something that would have, potentially taken, maybe, lots of coding can instead just be done by just a few clicks in the UI. So you can see that the precision and recall is much higher. And now you give it even more images. So 500 yes images and 5,000 images, and the precision recall inches even higher. Now you must be wondering how I gave it 5,000 images and 400 images using the UI. I did not. So this is where I ran into a limitation, where using the UI, it's kind of cumbersome to give it more than a handful of images. So you have to invoke the API or the software development kit that comes with custom vision for giving it a large number of images to train with. So the pros and cons of a UI-led model model building tool like Custom Vision is that it's great for a quick prototype model, but it's really hard to train with a large number of images. And the mitigation obviously is to use the SDK. Now, there's a Python SDK, there's a Java SDK, and there is another one, I forget, but there's multiple programming languages supported here. .NET is the third one. So the Custom Vision, this is the workflow if you were to use the SDK. You would install the Custom Vision SDK, and there's a great quick start tutorial that the Custom Vision service team has provided that you can use to do this. So you would install the Custom Vision SDK using pip install and Python, and you would also need a Python IDE. You could, like Jennifer said, spin up a data science virtual machine and just use Python Jupyter notebooks on that machine. You could even use the service. Microsoft has a service for Jupyter notebooks called notebooks.azure.com. So you could potentially use that in my case, because this is a very straightforward problem. I just ran Jupyter notebooks through Anaconda, which is another free install on my laptop itself. Once you've set up the environment, you'll have to authorize your model through your Python script by getting the training and prediction keys, and I'll show you that in a second, for your Custom Vision service so that the script can run against the Custom Vision service in your subscription. You then you separate the training images into separate lists, separate Python lists per the label, because remember that all of those images are in one giant file, all those labels are in one giant file, so you need to separate them out so that you can tell the trainer in Custom Vision that these are the yes images, these are the no images. Then you upload and tag the images, you train the classifier, and then you invoke the trained model through the predictor endpoint with test images. Finally, you prepare and submit the final output with all of the images that are a part of the test and holdout set. Now, if this looks too complex, don't worry about it. There is a really great tutorial available online. And then I've also written a script that heavily borrows from that tutorial and changes it to suit this competition. So remember, I talked about how you get the training and prediction keys for the service. This is where it appears in the UI. So when you instantiate the customvision.ai for your subscription, this is just a free limited trial subscription, and I'll show you some details about what exactly the limits of this kind of subscription are. You get a training key and a prediction key. So you use those two keys, and then you put it in your script, and then you upload and tag all the images. In this case, I have, so basically what you're doing here is some data management and some file management. You are taking the training labels from the training data that has been provided in the Kaggle dataset, and then you're ensuring that you create two separate lists with the yes images, two separate Python lists with the yes images and the no images. And you can see that most of the images are no images. Just ensure that these are the numbers that you should get once you have created these lists. Now, this is the second example that I showed you where I had about 100 images of each label. I wanted to do this quickly. It takes a few minutes once you invoke the training endpoint. For Custom Vision, this took maybe 3 or 4 minutes. With the 5,000 images, it takes longer than that. I just wanted to build a quick model. So I took 100 images of each label, and I invoked the training endpoint with those images. And when you do this, it's kind of scrolled off of the screen, but you provide the label along with the image for that particular class to the training endpoint. And then similar, so once you have that model trained, you get the test and holdout images as well. And again, I'm showing you the parts of the script that are not in the tutorial that the Custom Vision documentation has, because that's where you end up doing a little bit of work to build and run the model. So once you've done, once you've separated out the two classes, you've trained the model, you got your test and holdout images, you combine them, and then you predict the likelihood of oil palm for each of the images in the test and the holdout set. This is what those likelihoods look like, right? So final output should have 6,534 images. So that if you remember, the testing set has 4,356, the holdout set has 2,178, so that's about 6,500 images. And these are the scores that you'll finally get out of the custom vision predictor endpoint that you have trained. Now, at this point, it's up to you how you would want to determine, whether you give it a yes label or a no label. This is on the right, the screenshot that you see on the right is the type of format that the Kaggle submission is expecting for the competition. So the image name and just a 1 or a 0, that basically you're saying that this image has an oil palm or does not have an oil palm. So you can use the probabilities. I did a very straight up, comparison between the two probabilities for yes and no, and then I got this. I'll admit that towards the end there, I did a little bit of Excel manipulation because there's only so much patience I have doing file and data manipulation through Python. So I had this type of format on the left. I wrote it to a CSV file, and the rest of it, I just did it in Excel. So this is the submission site on Kaggle. Once you have that submission file created, which will look like this file on the right, as a CSV format with 6,530 rows, you will make a submission using the submit UI on the Kaggle site. And once you do that, it takes a couple of seconds. Now, if you wanted to check the precision, recall, and accuracy of your model, you would do that in the service itself. And because it runs cross-validation for you, it has a pretty good idea as to what the precision recall will be. When it comes to the test and the holdout set that you're submitting to Kaggle, there's no way of you to check that ahead of time. So you have to make that submission to Kaggle, and it takes maybe 1 or 2 seconds to compute what your score will be, and it automatically puts you on the leaderboard based on that score. When I did this, I think it was about a week ago or something, my position was 20 something, but now it's way lower because a lot of people have been submitting. And remember, you have 15,000 images to train with, right? So with 200 images, if you can get a score of 94% AUC, you can do a lot better with 15,000 images. So what does it mean to use Azure for custom vision services? The free tier, this is not the $200 credit. This is just a free tier that anybody can use even without invoking the $200 credit. Gives you the ability to create up to 2 projects. So each training, you can train multiple times in the same project, but you can have up to 2 projects. And there are 5,000 training images free and 10,000 predictions that it allows. And beyond that, if you're doing more than that, then there is a cost of 35 cents per 1,000 images, and here you can use your $200 credit to, to go above that 2 TPS if you wanted to do 10 transactions. So it's a little bit faster, and you can, train multiple times. You can create more than 2 projects. You can create up to 100 projects. So just for basic, for the sake of this competition, you could possibly even do this entire exercise that I showed. You could actually do this entire exercise that I showed using just the free tier without invoking your credit. Now, quickly, the hybrid approach would be if you trained your model using the compact. There are these domains that you have to select when you first define what kind of project you're running. And if you train your model using the compact domain, you can export it to one of these forms, such as TensorFlow, which will create a PB file, which you then download. And then you can run that TensorFlow model in Python by just taking the model.pb, which is the TensorFlow format, and the labels that it outputs. Not super useful as far as this competition is concerned, because you don't really have a lot of visibility into the values, the variables that it has used to train and create that model.pb. But if you're going down this path and teaching yourself how to use the custom vision service, this is something that will be useful to you in the future if you ever wanted to create an Android application or build machine learning models that are interoperable with TensorFlow. So beyond this, what would you do to get the score higher than what I got? You would use a larger training subset. You would use the confidence values. Remember that the labels that you got as part of the annotations had a confidence value, which I just ignored because I just used the labels. So you could use the confidence values for the labels, and then you could invoke the Azure Machine Learning service through the Python SDK. So this is the service on ML compute that Jennifer had also talked about briefly through the Python SDK. And if you want to go even deeper, you could do all this file and you could do all this portion with the file manipulation and creating your basic model. And then for the actual model creation, instead of using custom vision, you could use something else. This table is something that I found in a blog post that talks about the top 5 error rates for the ImageNet challenge, which is a standard benchmarking challenge for image classification. And you can see that ResNet and AlexNet is an older one, but ResNet was the winner in 2017. This was created by Microsoft researchers, and the custom vision service uses a variety of the different models, this being one of them. There are you might have heard of TensorFlow, PyTorch, Keras, Caffe. These are all very popular deep learning libraries that have image classification, options in them. So you could use those as well. So that's it for the presentation. We'd like to open it up to questions from the audience.
Fantastic. Thanks, Vani. And Jennifer and I, while you were speaking, have been quickly typing answers to the 10 to 12 different questions that we got during that. So if what we shared doesn't answer your question or you'd like more information, feel free to pop back on that thread so that we can clarify. And I'll just start moderating all these questions coming in. The first one is from an anonymous attendee. Do you have any particular suggestions for dealing with class imbalance? And Vani or Jennifer, you could chime in and unmute yourself, Jennifer, if you're going to.
Yeah, so there's a couple different ways to deal with class imbalance. It's a great question, first of all. 10 points to Gryffindor on that one. There's a couple different ways that are historically used in machine learning. So one is you can try to, actually, I'm not sure what the Kaggle rules are on this, so correct me, Meredith, if I'm wrong on this, but you can sometimes generate additional data by taking the images that you do have and cropping them, or maybe shifting a little bit, or making slightly different images using the data that you do have. So doing some artificial data augmentation with the classes that you have by taking it and rotating it a little, or making it slightly different, just so it can see other examples from the data that you do have. Then there are also a couple of algorithms that were developed especially to deal with highly imbalanced data sets. And those are, so there's a whole class of anomaly detection algorithms, and so that's used very often in problems like credit card fraud detection, where you have, if you think about, credit card fraud detection, that's a great example of having, any kind of credit card company is going to have a whole bunch of valid transactions, but then the number of fraudulent transactions are hopefully relatively small relative to the entire size of your database. And then known fraudulent transactions are going to be even smaller than that. So the Azure Machine Learning Studio does contain some, I think, 2 built-in anomaly detection algorithms. So that's something to check out. But if you wanted to do something like custom vision, you could also experiment with data augmentation as well.
Great. And to clarify, and I'm holding my little microphone just because somebody said the volume was a little bit low. Hopefully you can hear me. What Jennifer described in terms of getting creative and using the data and sort of dividing it up is totally allowable. We have a link to some clarification on using transfer learning and the rules about not bringing in external data. So if you have any additional questions, find that thread on Kaggle. But yeah, just to clarify, clarify, that is definitely an approach. And if anybody does that and would like to write about it, we would love to have you guest blog post. Great, and we have a whole bunch of questions coming in, so appreciate your patience as we read and then speak. So we have one coming in from Varun J, which says, which CNN architecture would you recommend apart from ResNet? How do you decide upon which models to try depending on the data set at hand? So sort of this magic behind when you're strategizing different ways to approach the problem. Do either of you have any words of advice on that?
I would say you should definitely try ResNet. That would be my first option, just because it's been performing so well, and most image classification problems in the last couple of years, most competitions are, it is outperforming everything else. If you look at the last slide that I showed with the, am I still sharing? So these are some of the models that has done well in the ImageNet competition. You could try some of these other ones. A lot of them are combinations. So after ResNet did really well, there was Inception ResNet. There's a bunch of other kind of ensemble of algorithms that are also performing well. So you could try some of those. So yeah, that's what I would suggest.
I would also just add that data science is a little bit science, but it's also a little bit art. So a lot of what we do is just guess and check and guess and check. So trying different models, trying it with different base models, see which one performs well, and then people publish results of, oh, this works really well. This architecture seems to work really well for this particular problem. So for me personally, I try multiple things usually, and I usually look for other problems that have been solved, similar problems that have been solved, and see what architectures they use. And I think a lot of others do that as well.
Yeah, I did that because even related to the class imbalance, because the training data was so heavily weighted towards the no images. At one point I tried training the model with the example I showed where I had 5,000 of the no images and 500 of the yes images. Interestingly enough, there was a warning that it's there. I mean, I didn't go into it in detail for lack of time, but there was a warning that the service returned saying that, hey, your classes aren't really balanced or something like that. You need to give enough number of samples for each class in order for us to do a good job of training the model, even though that's not what the training data set is like. So that's interesting that some of these algorithms expect you to provide an equal number of examples of each of the classes that you're trying to predict, regardless of what that real world data looks like.
Great. And in looking at the audience statistics, thank you everyone for filling that out. It's really exciting to see the diversity of students at various levels in their career, industry, government, nonprofit even, the one person from a nonprofit, and other. That's interesting. Please tell me what other was, because we thought we were pretty good at capturing in the 10 different choices, but would love to know. We have some very specific focus questions on different approaches, like let's try to group these scikit-learn, using Microsoft Computer Vision with potentially PyCharm IDE. Do you have some strategies in terms of lessons learned from using any of these specific approaches to share?
Do you want me to go first, Vani?
Yes, please do.
I can take a couple of these. Right. So just looking through the list here. So we already did the class imbalance one. How do you know which features in our data are the most useful for building a predictive model is the next question I see in order. So for this one, how do you know which features in the data are most useful for building a predictive model? So the beautiful part about deep learning is that you don't have to know which features in the data are the most useful for building the model. Like if you give it, here's a bunch of things, or like in the case of an image, you're basically providing that image, and the model actually can figure out what features are the most important. Now, you also bring up a fabulous, huge area of research in the machine learning community right now, which is transparency of models. So how, by virtue of that, these large neural networks that I described, it's really hard then to backwards figure out, okay, which part of the model, like what part lit up, what activated, what was it specifically that caused this to err more towards yes and no. And because it is very, very complex math under the covers, or it's just a lot of different variables all affecting it, it's combinations of them together, it can be hard to tease out that. So the area of transparency and trying to figure out more information about what actually caused different things is actually a huge area of research in the machine learning community right now. And it's a fascinating topic. So you can follow the latest papers on those. There's a lot of good stuff there. So I hope that was a useful enough answer, but if it isn't, just ping me. I'm happy to chat more about that for sure.
There's a question here about whether Microsoft Computer Vision works with PyCharm IDE. By Microsoft Computer Vision, I'm not sure if Mohammed Haris, you intend to ask about the service or about something else. The service itself will work with any IDE that supports Python, because essentially you're writing a Python script that is invoking the service. And if you are interested in just having PyCharm IDE set up for you, the data science virtual machine that Jennifer had talked about has the PyCharm IDE installed on it. So you can instantiate the data science virtual machine on Azure if you wanted to leverage that.
Awesome. I see another question here. Any suggestions for how to incorporate the confidence scores into the modeling process? So basically a lot of the machine learning algorithms that we've talked about, including custom vision, as well as different techniques. If you want to use a deep learning framework, this will also give you that. But essentially, they do incorporate usually the prediction as well as a probability score, or this confidence score on how confident they are in that particular prediction. So it's typically a number between 0 and 1. And you can treat that as a percentage too if you just times it by 100. And then you can utilize that to figure out how it is. So at the end of the day, it's up to you. Some of the things, one easy technique might be to figure out, or to use, if it's a basic classification, you could use anything above 0.5 count as predicting yes, anything below 0.5 count as predicting no. That's one option. If it's a one versus many classification thing, so a multi-class classification, where you're not deciding just between two options, yes or no, it's multiple options. You could see that, like with Vani's chart, one of the things that she presented back a couple of slides, when she showed the example of some of the data and what she transferred them to, there was one example where like it was very low confidence in both yes and no. It was like 1% confident or something that it was yes, and then a very low percentage that it was no as well. If you go back to,
it's 1.76.
Yeah, right there, exactly.
Yeah.
So that one is actually a really tricky one because it's really not confident either way. It really doesn't know. Right. And I think we ended up going with yes, but there's such a low confidence in that as well that's a tricky thing. So in general, if you're using confidence scores like that, like the bottom two are very, very easy because one is very high, one is very low. The top two are a little harder, and really the top one is the hardest, because the scenario, like if it's majority, if it's very strongly confident, like the second one, even no oil palms, I would pretty confident going with that. But it's really cases like that. And what I do when I see things like that is I would just go and crack open that image and look at it and be like, okay, what is it about this image that's making it very difficult for it to tell? And so if there's anything you can figure out, like if the lighting looks a little bit different, or you're trying to recognize pictures of animals, for example, which I do all the time on the AI for Earth team, or climate, weather patterns in satellite imagery or stuff like that. is it at a different angle, or is it an animal where like the majority of the animal is off of the screen and you just see like a tail or whatever, and so it's tricky to figure out. So things like that, where I would actually dive in and see if you can figure out a little bit more about that image and then do something to be able to do it. Because if it's something like bad lighting, then maybe you can mess with the image a little to help improve the quality of it.
Absolutely, that's great. And I just also want to point out that we shared also a link for the data page on Kaggle, and there's a paragraph with a link to actually an article from Figure 8 about their specific methodology for the confidence score, since these labels are crowdsourced from a number of contributors. We'll put that in the answer on the thread here, so you have it for your records also.
There's a question about whether scikit-learn can be used in addition to ResNet. Yes, you can try using scikit-learn. There is a good tutorial actually for predicting scores in the MNIST dataset, which is again a very standard benchmark recognition dataset that uses scikit-learn on the Azure Machine Learning Service. So you can look at that sample code as to how scikit-learn was used for that classification problem and see if you're able to, solve this problem using scikit-learn.
Awesome, and they keep coming. We are at the hour, so we're going to start focusing down, but I think some of these we really want to squeeze in. So one of them sort of goes a little bit meta. What does your typical workflow look like for keeping track of experiments or results? Vani, you mentioned you were up and running thanks to the UI in just 10 minutes, but can you maybe share some thoughts or philosophies about the challenges and opportunities in working in machine learning and data science, and sort of like that, how do you get in the headspace and keep it all organized?
That's a great question, because model versioning is one of those features, or I would just say it's just not a very mature environment right now for machine learning model versioning in some of these sophisticated tools that a lot of companies have created. It tends to be a manual process. In terms of the custom vision service, each time you invoke a new project, it just creates a new project. If that project already exists, it just gives it a new number, it appends a new number. The nice thing is that every time you run the trainer, it provides a new GUID for the iteration for that training instance. And when you can determine which of those training iterations have performed the best, and when you're running your predictor, you can invoke the specific training iteration. So custom vision does at least part of that for you. But if you're doing everything from scratch, then you need to have, I'm sure there are other tools out there.
Yeah.
Probably...
So the Azure Machine Learning Service that Microsoft provides actually does a lot of that for you. So I love using the Azure Machine Learning Service for that. That's one option that's there. But if not, to do it manually, the things that you need to keep track of are what data set did you use? So make sure you understand what subset of data fed it, what model hyperparameters you're using. So you trained it for this many epochs, and here's how many levels of kind of the shape of your neural network, how many nodes, how many hidden layers, that sort of thing. And then your results, like the accuracy numbers and stuff. So if you need to do it the old-fashioned way, just crack open a big spreadsheet and you can store everything off there to help you stay organized.
So the question about overfitting, so overfitting generally happens when the model that you have created does really, really well on the training data that you have used to create the model, but it doesn't do too well when it is being asked to predict data that it has never seen. So it's a good question. In this particular case with the oil palm plantation, the risk of overfitting is clearly because we have so many files. There's a pretty big class imbalance where there's a huge number of files with the no oil palm. So that is something you need to be sensitive to. I don't know, I don't know about how you would mitigate that. I think it happens when you're trying to really fine tune your model. In this particular case, since the test and the holdout data, is very similar to the training data, it is hopefully not too much of an issue, but I definitely noticed that the test and holdout data were not performing as well as the k-fold cross-validation that custom vision was performing on. Jennifer, do you have any additional thoughts on that?
Yeah. So, I mean, we talked about the training and the test set, and there's also something called a dev set. There's kind of an intermediate one as well that you can use for training, like your model parameters, your hyperparameters, and then your test data. But overfitting essentially just means that your model is very optimized for the training data. So it's really good at predicting that, but when you try to have it generalized to data it hasn't seen before, that like the test set, it is not doing so well. So that means you almost made it too specific to that training data. And so there's a number of standard techniques to deal with that. One of them is something called dropout. So dropout is something that you can do in neural nets, and a lot of the deep learning frameworks have built-in functions to help do this. But essentially you kind of randomly throw out some data, and that helps you, even though that sounds kind of crazy, it helps it become a more generic solution and not be completely fit to just what's in there. And there's a number of other techniques as well, but that's a really quick one. But let me know if that's not helpful. I'm happy to chat further.
Absolutely. And one of the ways that you could do this creatively, and there's been some discussion at our Datathon Collaboration Day that we hosted a couple weekends ago, for example, is, we provided as the WiDS Datathon Committee the 15,000 images in the training, zip file, and then there's a certain amount for the testing and so forth that decides the public leaderboard. You can creatively chop up and reallocate, sort of pretend, just like Vani was noting, that only work with a certain portion of those 15,000 images, and you can imagine setting up some interesting tests for the robustness of your approach, essentially using some of that training data to test and validate and iterate.
Absolutely.
So there was a question about leveraging the confidence interval in the training data. I don't know if there's any standard mechanism. The way I would leverage that is remember the example that Jennifer pointed out in my slide, which didn't do a really good job. It wasn't really sure about whether or not, there's this image has oil palm or not. I would go back and look at the confidence in the training data and see whether there is, this type of very close, if the confidence interval is very similar, then and then change the labels instead of just giving it, just using like brute force. I would change the labels a little bit to see if it does better on images like this, where the confidence of the prediction goes up. So that's one way I would tackle that. By isolating the images that do not get predicted with high confidence and just rerunning the training by taking a closer look at the confidence interval in the training data.
Awesome, thank you. And thank you for the messages from folks. If you sent it to all panelists, we see it, but then everyone else doesn't. I just wanted to mention some of them. They say, I've learned so much in this past hour and have the confidence to tackle this challenge as someone completely new to all of this. Thank you so much, with all caps. That's super exciting for us to hear. I see on the audience stats that there's 57% of folks who have not done any sort of machine learning, cloud computing, image analysis competition before. You are in good company. Last year when we did the Datathon for the first time using some text data from Bill and Melinda Gates Foundation, it was 70% had never done a Kaggle or machine learning competition before. So we're really excited that some folks new to this are competing for the first time. Thank you very much. And people are noting that they're excited to teach themselves more about all of this, and I'm sure that Vani and Jennifer will continue to provide additional thoughts on social media, and we'll be posting all of the content, the slides, the video on the WiDS Datathon website. Jennifer and Vani, do you have any parting thoughts as people are looking at, you know, the deadline to sign up, February 21st, and the exciting announcement that we will be providing a certificate of achievement for everyone scoring 95% or higher? Any sort of parting words of advice?
My advice to everyone would be that when I try something that I have no idea how to solve it, I take on a really hard problem, that's when I learn. And so I'm super excited for all the people here that are saying, you know, I don't really know anything about how to do this, but I'm just going to try, because that's where you grow and learn, right? Is when you do something that you don't know how to do, and then you have to figure it out. So, so excited. This is a good step for everyone. It's always a good to take on a Kaggle challenge. So congratulations, good luck, have fun.
My advice would be, a lot of times people are like, oh, I need to teach myself how to run convolutional neural networks. I need to teach myself computer vision. I'm going to sign up for this online course. Having a competition is a great way to teach yourself, because it's date driven, and you know, you really have, once you sign up, you have some motivation to solve it. So definitely leverage the opportunity. This is a relatively simple challenge. There's a lot of image classification challenges where you have to do a ton of image manipulation before you can even give that image data to the trainer. But in this case, the organizers have done a great job of giving you, you know, really the right size of images that a lot of these algorithms expect. So definitely give it a shot if you have never participated in a Kaggle competition, or if you have never really, you know, run a deep neural network or given yourself a chance to leverage transfer learning or any of that great stuff. So good luck, and thank you for joining this call, and thank you for giving us an opportunity to get to know some of you. Thank you.
Great. And on behalf of the WiDS Datathon Committee, we so appreciate your interest. I'm super impressed that so many people stayed on past the 1 hour mark. That's dedication. Go for it with your entries, form those teams, and we are really excited to announce, you know, we'll have first, second, and third place winners on stage, but so many people are just going to benefit from this experience, and we love hearing from you. So don't be shy in reaching out to widsdatathon@stanford.edu and using the hashtag to connect with everyone else who's working on this globally. All right, take care.